Now in this section, we are going to explore how light interacts with matter and why this is so important, not just for life on Earth, but also for understanding the universe. So before we dive into the physics, let's start with a simple question. What would happen if light didn't interact with matter at all? Could we see? Could plants grow? Could life exist? Let's find out. Alright? Now think about plants. They rely on sunlight to produce energy through photosynthesis. And if light couldn't interact with the molecules in leaves, photosynthesis wouldn't happen, right? And what does that mean? That means no grass, no wheat, no tofu, no beef, basically no food chain as we know it. In other words, light interacting with matter is literally the foundation of life. And these interactions let us breathe, see, and survive. So every time you read these words on your screen or look around your room, you are observing light interacting with matter. Light bounces off objects, enters your eyes, and triggers signals that your brain interprets as images. So without this interaction, the world would be completely invisible to us and survival would be impossible. Now let's think beyond Earth. Astronomers can't touch a star or travel to a galaxy millions of light years away. But they can observe the light those objects emit. So each atom and molecule interacts with light in a unique way, leaving specific fingerprints in the spectrum. So by analyzing these patterns, scientists can figure out the composition, temperature, and even motion of stars and galaxies, all from here on Earth. Now here's a simple illustration to connect both ideas. Sunlight reaches Earth, interacts with planets to produce food, and also reaches us so we can see our surroundings. And the same principle, light interacting with matter, is what astronomers use to read the universe. Just as light tells us about life on Earth, it also tells us about distant stars and clouds of gas in space. Now to summarize this slide, light interacting with matter is essential for life, vision and survival. And it's the key to decoding the universe. So keep this idea in mind as we explore the details of electron excitation, emission and spectra in the following slides. And without these interactions, neither life nor astrophysics would be possible. Now let's start looking at the atoms themselves. So to make things simple, we will begin with hydrogen, the simplest and most abundant atom in the universe. So using hydrogen as our model will help us understand the basics of how electrons absorb and emit light before we move on to the more complex atoms. So hydrogen has one proton in its nucleus and one electron orbiting around it, and that's it. So imagine a tiny positively charged center with a single negatively charged particle moving around it. Because it's so simple, hydrogen is like the perfect training example for understanding how light interacts with atoms. Now starting with hydrogen allows us to focus on the basic principles without getting lost in complexity. Once we understand how one electron absorbs or emits light, we can apply the same concepts to heavy atoms with more electrons and more energy levels. It's like learning to walk before you run. But hydrogen is not just simple, it's everywhere. Around 90% of all atoms in the universe are hydrogen. And that means the light we see from stars, galaxies and nebula is dominated by hydrogen atoms. So studying hydrogen gives us insights that are universally applicable. It's literally the building blocks of most matter in the cosmos. So take a look at this model on the hydrogen atom. You can see the proton at the center and the electron orbiting around it. And when light interacts with this electron, it can jump to a higher energy level or fall back down emitting light, right? Now that we understand hydrogen as our model atom, let's talk about energy levels, the shelves that electrons occupy, and how electrons move between them. So, this is key to understanding how atoms absorb and emit light, which creates the spectra we observe from stars and galaxies. Now, electrons are not free to float anywhere around the nucleus. They can only occupy certain allowed orbits called energy levels. And the lowest, most tightly bound orbit is called the ground state. Think of it as the electron's home, stable and comfortable. And when the electrons absorb energy, it can move to a higher orbit, an excited state. And these are less stable and temporary. So the electron will eventually want to fall back down to the ground state, releasing the energy it absorbed. Now imagine you are moving a book from a lower shelf to a higher shelf. The higher the shelf, the more effort you need. And similarly, the electron needs exactly the right amount of energy to jump from one energy level to the another. Too little or too much energy and the jump can't happen. So check out this diagram of a hydrogen atom. You can see the electron jumping from the ground state to higher energy levels, and each arrow represents the exact amount of energy needed to make that jump. So this is the physical process that creates absorption and emission lines in spectra. Now in hot gases, atoms move rapidly and collide often, and these collisions can knock electrons into higher energy levels. So this is one common way atoms becomes excited in stars and other hot cosmic environments. And there's a second way. So the second way is by absorbing a photon, which is a bundle of light with a specific energy. And only a photon with the exact right energy can excite the electron to a particular level. So this is why each atom has a unique fingerprint in its spectrum. Only certain wavelengths are absorbed or emitted. Now to summarize, electrons occupy fixed energy levels, moving between them requires energy, and atoms can be excited either by collisions or by absorbing photons. So these basic rules form the foundation of how we interpret the light from the universe. Alright, now that we know how electrons get excited to higher energy levels, let's explore what happens next. How atoms absorb or emit photons. So this is the heart of how light carries information about atoms in stars and galaxies. Now electrons can only absorb a photon if its energy exactly matches the energy difference between their current level and a higher level. So think of it as needing a key that perfectly fits a lock. Only the right photon can unlock the jump to the higher orbit. So if the photon has too much energy or too little energy, then the electron simply ignores it. So this selectivity is what makes each atom's absorption spectrum unique. Only photons with very specific energies are absorbed. But these excited atoms don't stay that way for long. Usually, within a billionth to a millionth of a second, the electron will fall back to a lower energy level. So the atom wants to return to its stable state, just like a ball rolling back into a valley after being lifted up a hill. And as the electron drops down, it releases the extra energy in the form of a photon. And the wavelength of this photon corresponds exactly to the energy difference between the levels. So this is how atoms emit light at very precise colors or wavelengths. So every type of atom has its own unique set of energy levels. That means every element absorbs and emits light in its own pattern, its atomic fingerprint. Therefore, by studying these patterns in the light from stars, astronomers can tell exactly which elements are present even in galaxies millions of light years away. So again, look at this sequence showing photon absorption and emission. You can see electrons jumping up when absorbing a photon, then falling back and emitting a new photon. So each jump corresponds to a precise energy, and this is exactly how we decode the light from the cosmos. So atoms absorb photons only with the right energy, and excited atoms quickly release energy as photons. So each atom has a unique spectral fingerprint. Now so far we have talked about how electrons absorb and emit photons, creating specific wavelengths of light. Alright, now let's see a real world example you encounter every day, neon signs. So this will help connect atomic physics to something tangible. Now when electricity flows through the neon gas in a sign, it causes collision between electrons and neon atoms. And these collisions give electrons in the neon atoms enough energy to jump to higher energy levels. So just like we learned before, these excited electrons don't stay up for long. They fall back down, releasing their extra energy as photons. Now each photon has a very specific wavelength which determines the color we see. And pure neon produces a reddish orange color, which is why classic neon signs look like that. But other gases like argon or krypton emit photons of different energies, producing blue, green or other colors. So even signs called neon signs may use a mix of gases to create a variety of colors. But the principle is always the same. Electrons absorb energy, get excited and emit photons as they return to the lower levels. Now the cool part is that the same physics used to make neon glow is exactly what astronomers use to study distant stars. So by analyzing the light from the stars, we can see their atomic fingerprints and learn what elements they contain, all without leaving Earth. So look at these neon signs glowing in different colors. Each color corresponds to specific photon energies, and each gas has its own unique set of energy levels. And this is a practical example of atomic spectra in action. So neon signs work because electrons absorb energy, get excited and release photons as they fall back down. And the colors depends on the type of gas. So this is a direct everyday example of atomic spectra in action, the same process astronomers use to study stars. Alright, now so far we have looked at how electrons absorb and emit photons in atoms. Now let's explore why hot objects, including stars, glow and how this connects to the light we see from them. So remember, the visible surface of a star is called the photosphere. And this is the layer dense enough to emit lots of light, yet transparent enough for that light to escape into space and reach our eyes. And the layers beneath the photosphere emit light too, but much of it is absorbed before reaching the surface. So the light we see comes primarily from this outer layer. Now think of a stove coil. When it's just starting to heat, it glows red, and that's cooler than yellow or white. And as the coil gets hotter, it glows brighter and changes colors toward yellow or white. So stars work the same way. Their temperature determines the color of the light they emit. For example, the Betelgeuse appears red because it's cooler, while Regal appears blue-white because it's hotter. Now the light emitted from hot objects comes from accelerated charged particles, usually electrons. And when their motion changes, it produces electromagnetic waves, which are photons of light we detect. So stars glow because their hot gases have moving electrons that constantly accelerate, generating the light we observe from millions of kilometers away. So now we know stars glow. Why? Because they are hot and the photosphere is where light escapes. Now hotter objects emit brighter and bluer light. So all of this happens because moving electrons produce electromagnetic radiation. So this principle will help us quantify stellar light next. Now we have seen that stars and hot objects emit light. So let's explore black body radiation, which is the type of light emitted by any objects due to its temperature, including stars, stoves, and even light bulbs. Now, a black body is an ideal object that absorbs all radiation that falls on it and emits radiation efficiently at all wavelengths. And that being said, real objects are never perfect, but many, including stars, behave closely enough like black bodies for us to use this concept. So the sun and the other stars emit light in a way that's very similar to a black body. Their emitted light depends mainly on their temperature, which allows astronomers to calculate properties like energy output and color. And black body radiation is not limited to stars. A light bulb filament also glows because it is hot, and lava also glows red, and even an ice cube emits infrared radiation, though we cannot see it with our eyes. So as long as the object has a temperature above absolute zero, it contains thermal energy, and that energy is constantly radiated as electromagnetic waves, which is why we can detect it with sensors, cameras, or even our skin in the case of warm objects. Now notice here, the light bulb filament illustrates a hot glowing object, and the sun shows a natural example of black body radiation. Now you can see the connection between temperature and the intensity and the color of emitted light. Now what we just learned, hot objects emit black body radiation, and the sun and stars are excellent examples, and all objects above absolute zero radiate energy. So this gives us a foundation to understand how astronomers calculate energy output and temperature from distant stars. Alright, so let's see how we can quantify the total energy emitted by a hot object using the Stefan-Boltzmann law. And this is crucial for understanding stars, their brightness and energy output. Now here's the key idea. As an object gets hotter, it doesn't just emit a little more energy, it emits a lot more. So energy output rises very quickly with temperature, and the energy emitted per area is proportional to the fourth power of temperature. So the equation is E equal sigma T to the power 4. So this is called the Stefan-Boltzmann law. So here E represents the energy emitted per second per square meter of the surface, and T is the temperature in kelvins. And notice the fourth power. So doubling the temperature makes the emitted energy 16 times greater. Now here sigma, it is called the Stefan-Boltzmann constant. It is a fixed number that helps convert temperature into energy units. So it lets us calculate how much energy a star like the sun emits per square meter of its surface. Okay, we will do an example next so you will know how to use the formula. Now for example, the sun has a temperature of about 5780 Kelvin. So using the Stefan-Boltzmann law, we can find that each square meter emits more than 63 million joules per second. And that's an enormous amount of energy radiated into space. Okay, let's look at this graph. You can see how hotter objects have more intense radiation across all wavelengths. The area under each curve represents the total energy emitted, and the hottest objects clearly emit the most energy. Alright, let's put the Stefan Boltzmann law into practice with a real example, the sun. So let's calculate how much energy is emitted by 1 square meter of the sun's surface. So follow along step by step and you will see how astronomers use this law to understand stellar energy output. Now first we write the formula E equals sigma T to the power 4, where E is the energy emitted per square meter and sigma is the Stefan Boltzmann constant and T is the temperature in kelvins. Now we are asked to find the energy E, and we know the temperature and sigma is just a constant. So we can calculate E just by substituting these numerical values to the equation. Temperature is 5780 Kelvin, right? And Stefan Boltzmann constant is given. So you just have to plug in the numerical values into this equation. So now let's raise the temperature to the fourth power. That means 5780 to the power 4. So this step shows how dramatically energy increases with temperature because of the fourth power relationship, right? And finally multiplying by Stefan Boltzmann constant, we get energy is equal to 6.35 times 10 to the power 7 joules per second per meter square. And that means each square meter of the sun's surface emits roughly 63.5 million joules per second. So that's an enormous amount of energy, and it shows why the sun can light up and heat the entire solar system. Alright, now that we have seen how much energy stars emit with the Stefan Boltzmann law, let's explore how the temperature of a star affects the color of the light it emits. And this is where Wien's law comes into play. So by understanding this law, we can actually measure the temperature of stars just by looking at their color. Now as we already said before, hot objects emit most of their radiation at shorter wavelengths, which appear blue. So think of a very hot stove coil. It glows white or bluish because the particles are moving so fast. But in contrast, cool objects emit more at longer wavelengths, which appear red. So a cooler stove coil glows red, or like Betelgeuse in Orion, which is a red supergiant star. Now Wien's law tells us the wavelength at which a hot object emits most of its light. In other words, it predicts the peak color of the radiation based on the temperature of the object. So hotter objects peak at shorter wavelengths, that means bluer light, and cool objects peak at longer wavelengths, that means redder light. So the equation is lambda max, maximum wavelength, is equal to 2.90 times 10 to the power 6 divided by temperature in Kelvin. So lambda max is the wavelength of maximum emission in nanometers, and T is the temperature in kelvins. Now the famous examples are Betelgeuse and Regal in Orion. So Betelgeuse is cooler than the sun, so its peak wavelength is longer. Therefore, it appears red in the sky. But Regal on the other hand is much hotter with a peak at shorter wavelengths, giving it a bluish white appearance. Now you can see the contrast clearly when you look at Orion's stars. So this is incredibly useful. So by measuring the color of a star, we can estimate its surface temperature without ever traveling there. And combined with the Stefan Boltzmann's law, we can even determine the star's luminosity and energy output. Now to summarize, Wien's law links temperature and color, letting astronomers read the thermal properties of stars from afar. Now let's apply this knowledge to an example problem to see the law in action with real numbers. Okay? So let's calculate the wavelength of maximum emission for the sun and understand what this tells us about the color of the sunlight. Now first recall the Wien's law. Lambda max equal to 2.9 times 10 to the power 6 divided by temperature in Kelvin. Now we know the sun's surface temperature is 5780 Kelvin. So let's plug in this into the equation. T equals 5780 Kelvin, right? So by calculating, you should get the peak wavelength of sunlight around 502 nanometers. And 502 nanometer is in the green-yellow part of the visible spectrum. So you can open the electromagnetic spectrum and focus on the visible spectrum. Then you can see 502 nanometer is in the green-yellow part. But sunlight appears white to our eyes. Now why is that? Do you know why? Because this calculation shows it is in the green-yellow part of the spectrum. But we see it white in our eyes. So why is that? It's because it's actually a mixture of all visible wavelengths, not just the peak. So this is just a peak wavelength, right? But it has other wavelengths also. So it's a mixture of all visible wavelengths, not just the peak. So this is why sunlight looks white even though the peak emission is green-yellow. Alright, now with this we conclude the second section on interactions of light and matter. So let's quickly summarize what we learned so far. So light interacts with atoms, allowing electrons to move between energy levels. And excited atoms emit photons with specific wavelengths, creating unique atomic fingerprints. Next, hot objects including stars emit black body radiation, and their temperature determines both the total energy emitted, which we can find using Stefan Boltzmann law, and the peak wavelength of light, which we can find using the Wien's law. So by studying these interactions, we can determine the temperature, composition and colors of stars without ever visiting them. So with this, we have the tools to understand how astronomers read the light from the universe. So section 3 will build on this to explore spectra in more detail.